So, entropy is statistical, and I think it might be appropriate now to look at the part of that video that explains exactly what entropy is. That is, how statistics explains entropy.
Well, let's consider two small metal bars, one hot and one cold. For this simple model, we'll consider only 8 atoms per bar. Each atom vibrates according to the number of energy packets it has. The more packets, the more it vibrates. So let's start with 7 packets of energy in the left bar and 3 in the right. The number of energy packets in each bar is what we'll call a state. First, let's consider just the left bar. It has 7 energy packets which are free to move around the lattice. This happens non-stop. The energy packets hop randomly from atom to atom, giving different configurations of energy. But the total energy stays the same the whole time. Now let's bring the cold bar back in with only 3 packets and touch them together. The energy packets can now hop around between both bars, creating different configurations. Each unique configuration is equally likely. So what happens if we take a snapshot at one instant in time and see where all the energy packets are? So stop. Look at this. Now there are 9 energy packets in the left bar and only 1 in the right bar. So heat has flowed from cold to hot. Shouldn't that be impossible because it decreases entropy? This is where Ludwig Boltzmann made an important insight. Heat flowing from cold to hot is not impossible, it's just improbable. There are 91,520 configurations with 9 energy packets in the left bar, but 627,264 with 5 energy packets in each bar. That is, the energy is more than 6 times as likely to be evenly spread between the bars. But if you add up all the possibilities, you find there's still a 10.5% chance that the left bar ends up with more energy packets than it started. So why don't we observe this happening around us? Well, watch what happens as we increase the number of atoms to 80 per bar and the energy packets to 100, with 70 in the left bar and 30 in the right. There is now only a 0.05% chance that the left solid ends up hotter than it started. And this trend continues as we keep scaling up the system. In everyday solids, there are around 100 trillion atoms and even more energy packets. So heat flowing from cold to hot is just so unlikely that it never happens.
So yeah, energy does spread out. Energy does even out. Here I've got a TV dinner. I got this because I wanted to show you something that I know you're aware of. When you put this TV dinner in the microwave, you are hitting it with low entropy energy. And as you know, something in a microwave does not heat evenly. So what is part of the instructions? Right here it says, let's stand 2 minutes. Put that up here so you can see it maybe, right here. Let's stand 2 minutes. Why? So the heat can even out, because that's what it's always going to do. If we're around in 2 billion more years, what's printed on that box, let it stand for 2 minutes, will still be valid. Because what did the guy say about the statistics?
So heat flowing from cold to hot is just so unlikely that it never happens.
I love that part. I'm going to play it again.
So heat flowing from cold to hot is just so unlikely that it never happens.
Don't forget that part. We're going to talk about it some more. This is in the same video with this clip.
Jeremy England takes this one step further. He's proposed that if there is a constant stream of clumped up energy, this could favor structures that dissipate that energy. And over time, this results in better and better energy dissipators, eventually resulting in life. Or in his own words, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant.
So on one hand, it's so unlikely it never happens. And on the other hand, it's so unlikely, but there's always a chance. given enough time. If you haven't noticed, I want to point out the selective reasoning, the selective use of statistics. Yeah, we're going to talk some more about this.